Hello and welcome to Critical Thinking Lecture 11. Today we're going to be talking about inductive arguments and John Stuart Mill's methods in particular. Now, we'll start here with inductive arguments. First, I want to talk to you about risky arguments. Now, recall a valid argument, one such that if the premises are true, then so is the conclusion. You can think about validity as meaning no risk. Now, that just means, like, if you have premises and conclusions set up correctly, then you can be sure about the conclusion, right? There's no risk there. There's no divide or gap between the premises and the conclusion. Of course, this doesn't mean it's sound. You got to make sure that the premises are true if you want to get a valid argument that leads to a true conclusion. But in any event, valid arguments are deductively good, right? Like you can just immediately deduce the conclusion if you have the premises. That's what validity means. Now, not all arguments, of course, have this feature. Scientific inquiry, for instance, progresses by constructing hypotheses that we're not sure if they're true, and we make inferences based on them that are sort of outstrip the premises that we have. We can only, for instance, inquire into a small portion of reality at a time. So cosmologists, for example, assume what's called the Archimedean principle, which is that the laws of nature operating within our light cone are the same as those outside our light cone. Now think about the evidence we have for this. We just have information about our light cone, and now we're making hypotheses that outstrip that premise or outstrip that information, and basically asserting or assuming that these laws apply in places we've never been. It's somewhat of a risky argument. Now, look, there are a couple of other examples, sort of standard examples of risky arguments. Here's one. There are 20 oranges in this bag. 12 have been inspected and are delicious. From this, you might think it follows most of the other 8 oranges in the bag will be delicious. How about this one? There are 20 oranges in the bag. This randomly chosen orange is delicious. Hence, most of the remaining 19 oranges will also be delicious. This is the sort of reasoning we work with all day, every day, most of the time, as a matter of fact. Now, we think about proportions, and we can make this precise. So, think about what most means. In most of the oranges in the bag will be delicious. Now, I suspect this is going to be contextual, right? If you get oranges from a place that traditionally has bad oranges, right? Maybe you want to adjust your data here, or your percentage here, right? Or your proportion. Now, you can also think of other contexts not involving oranges, right? What does most mean in most people in the U.S. will be infected by SARS-CoV-2? Is it 90, 80, 50? So think about most of other 8, most of the remaining 9. Now I just picked some examples or some specifications of the probability that seem plausible to me. Now, this might seem like a strong argument to you, or it might seem like a weak argument to you. In any event, this is a way to precisify what we mean by using probabilities and proportions. Now, all this sort of stuff, especially like the scientific motivation behind it, is in the service of a general project that consists of 3 parts: retrodiction, explanation, and prediction. Now, not all risky arguments concern samples and inferences. Researchers often make retrodictions or hypotheses about what's happened in the past. For example, physicists believe our universe began with a big bang. Now, researchers often look towards the future and make risky claims too. These are predictions about what might happen. For example, researchers predict that at our current rate of carbon emissions, we're not going to be around any in the future, right? It's a prediction. Now, researchers also, this is something that maybe you've not heard of, but researchers also produce explanations or plausible links between retrodictions and predictions that are supported by data. Einstein's a great example of this. He reviewed data concerning light, fundamental particles, and gravity, as well as problematic predictions made by physicists of his day. All in the interest of providing a unifying explanation for the data that led to a different set of predictions that avoided the problems. You can make hypotheses about what happened and hypotheses about the future, but what we also need are mechanisms linking the two together. And we need good mechanisms, because if you have that, then you can make better predictions. But we need all 3. Retrodictions feed into explanations. And you can use explanations and predictions to figure out what you should expect in the past. We do this today. We have, for instance, data and explanations and predictions that we've made about radioactive particles and how they emit energy. And we can use this to make inferences about what happened in the past, like for instance how old bones are, or fossil fuels using carbon dating. Now we can also go in another direction. If we don't have an explanation, we can use retrodiction, like verified retrodictions and predictions, to provide an explanation. Now this was the example of Einstein, right? Providing that mechanism that linked the two together, these retrodictions and predictions. Now similarly, we can use retrodictions and explanations to fill out this grayed out bubble of predictions. We do this a lot, like when for instance, when we think about how consumers purchase goods at certain times of the year. Like if we understand the mechanisms why people are driven to purchase goods, and we've used these models to explain behavior in the past, we can make plausible predictions about their behavior in the future. Now, let me jump over here to Mill's methods. John Stuart Mill, genius. He constructed methods that he thought governed the sciences. They'll be very helpful for us, and hopefully for you as heuristics when you're thinking about your life, because it's not just applicable to sciences. We'll start with this illustrative example. Okay, now John, Sally, Frank, and Otto, they all went out to dinner the other night. There were oysters, beef, salad, and cake on the menu. Not everybody ate everything, but if you look over here in the far corner, everybody got sick. Now, what we're going to do is we're going to try to figure out what was the culprit. We'll use John Stuart Mill's method of agreement, he called it. If in all cases where an effect occurs, there's a single factor that is common to all those cases, then C is the cause of the effect. And this is part and parcel of Mill's methods, right? He's looking for causes. So not correlations, but causes. Check it out. Oysters. Everybody ate oysters. This is not the case like for cakes and salads and beef. So everybody who ate oysters got sick. Common cause. Looks like oysters are the culprit, right? Okay, that's one. Now, let's check out difference. Method of difference. If you have one situation that leads to an effect and another which does not, and the only difference is the presence of one single factor C in the first, we can infer C causes the effect. Here's a sort of setup similar to the previous one, but I've changed some of these yeses and nos, right? Like, so here everybody's had the oysters. Here everybody's had the beef. Here everybody but Otto's had salad, and everybody's had the cake. Now, everybody was sick except Otto, right? Check it out. Otto didn't eat the salad. Otto didn't get sick. What do you think was the cause? Dun, dun, dun. Salad. That's the method of difference. Now we can combine these. In all cases where an effect occurs, there's a single factor that's common to all, and C is the cause. If you have a situation that leads to an effect and another which does not, the only difference being the presence of C, then C is the cause. Putting them together, check this example out. Again, I've adjusted the yeses and the nos. Here, everybody's had oysters. Here, everybody but Otto's had beef. There's a different distribution for salads and cakes. And, of course, Otto got off scot-free. No sickness for Otto. Now, check it. Otto did have the oysters. Didn't get sick. Okay, so we can rule out the oysters. And, of course, we don't even need to talk about Otto in this case anymore. Now, thinking about sick. Everybody here is sick. What did they have? All right, well, look, check it out. Sally, she didn't have salad, but she got sick. Frank didn't have cake, but he got sick. Looks like we don't need those. Must have been the beef. Method and difference. Now, this is a more complicated one, probably one that occurs more frequently. This is the method of concomitant variations. If across a range of situations, so not just one event, but a range of situations that leads to a certain effect, we find a certain property of the effect varying with variation in a factor C that's common to all those situations, then we know C is the cause. All right, let me walk through this one a little more slowly. Again, different setup, although here everybody's sick and everybody ate everything, right? So it doesn't look like the method of agreement or difference is going to help us, right? But let's think a little harder. In this case, John and Sally got a little sick. Frank got very sick, and Otto is unfortunately critical in this example. Now, they all had the same amount of cake. All right, well, then that won't help us. And similarly, they all had the same amount of beef and salad. Well, okay, that won't help us either. Let's see. Fingers crossed. What are we going to do? Let's look at the oysters. Now, John and Sally had 1. Frank had 4. And Otto had 12. What do you think is the culprit? You're right. It's the oysters, concomitant variations. The thing that the oysters, the frequency or the number of oysters that people ate varied in the same degree to some extent with how sick people got. So using this method, you can determine that it's the oysters, and the oysters to a large degree that were the cause of the sickness.